This set of slides introduces the idea of the control of gene expression by means of unique connectrons. Connectrons are redundant if the C1, C2, the control RNA sequence sources, are produced by the same or different transcripts of the same DNA. And if they produce target T1, T2 scopes that control the expression of the same set of gene coding or non-coding DNAs. Perhaps this graphic will give you some sense. So a redundant connectron is one where for a given transcription element, whether it be a gene coding or non-coding, there are several source ranges of C1s and C2s, the RNA sources, and that these produce a different range of T1 target sequences and a different set of T2 target sequences. But a unique connectron for a given transcribing region has only one C1, C2 source range, and that produces only one T1 and one T2 target range. So the redundant, there are many different ways that connectrons can be generated, and unique, there's only one. Okay, that's just a general sense. There's a variation on this, of course, and that is that there can be a mixture of control regions where this information is produced, and then a mixture of target regions in the redundant connectrons. In the unique connectrons, there's only one range where the RNA is produced that acts to form the loops on the target sequences. Again, the sources and the targets can be on the same chromosome or on different chromosomes, intra and inter. The balance between intra and inter-chromosomal connectrons is that they're in the mouse transcriptome from Reichen, there are 113,000 unique connectrons, and about 49,000 of those are intrachromosomal, whereas there are 64,000 that are interchromosomal. This shows the length of the chromosomes. In this graphic, I had introduced the mitochondrion as the 20th chromosome, and that X and Y as 21 and 22, and because I wanted to study whether mitochondria produced connectrons. So you see that in general there's a linear drop-off in the size of the chromosomes. So that's the ancient sorting method from the physical days. If you look at the number of connectrons produced by the different chromosomes, you see that the total number in blue goes like this, and it varies in some small way as a function of the length of the chromosome. But for example, chromosome 4 in mouse has a huge number of connectrons, and that many of these are intrachromosomal, that's the pink line, and that the pink line, the intrachromosomal, often determine the maximal condition of the total. And then the yellow line is the chromosomes that send the number of connectrons sent by chromosomes, and they're receiving interchromosomal numbers. So this graph is rather interesting. Distribution of chromosomes by type. Again, this just sorts out the total and the intra. You can see how chromosome 4 and chromosome 17 are very important. Distribution of connectrons by type. Again, this sort of sorts out this thing. The blue line is the connectrons sent from a given chromosome, and the pink line is the number of connectrons received from a given chromosome. The graphic here shows the redundant connectrons as a function of redundant connectrons, and whereas this graphic shows the unique connectrons. Now the intrachromosomal things here look like they're zero, but they're not really. They're just very low. So that these intrachromosomal connectrons dominate the numbers, whether they're redundant or whether they're unique. So certain chromosomes have high redundancy. I mean, there's almost an order of magnitude difference between the number of unique and redundant connectrons, as we just saw in the graph before. That chromosome 4, X and Y have high redundancies, and chromosomes 7 and 12 are slightly less redundant. The unique connectrons are presented here, and again the intrachromosomal unique connectrons are very large, whereas the inters are much smaller. The greatest number of unique connectrons are intrachromosomal, and again there's an order of magnitude difference. This is the unique connectrons. So this is the unique connectron cross-chromosomal matrix, showing the very large numbers for the but now if we clip the graphic and the intra things become huge mountains, and now the low-lying interchromosomal things pop up. And then if we clip out the diagonal so it doesn't bother us visually, you see there's a general falling off in this dimension, which is the size dimension of the chromosomes. But there's a fractal pattern here in the transmission direction, and that in general every chromosome exerts connectron control over every other chromosome except for the Y. This cuts out the interchromosomal connectrons, but this shows that every chromosome sends connectrons to the X chromosome and to the Y chromosome, and the Y sends to X, but it's only the X chromosome that sends back connectrons to the 19 chromosomes. So X and Y chromosomes are clearly different as far as connectrons are concerned. Chromosomes 1 to 19 send connectrons to X and Y. X sends connectrons to Y, but no. But it's the Y chromosome that sends connectrons to the X chromosome, and just one connectron. Oh, I see. So X sends to the 19, and Y sends only to X, and just one connectron to chromosome 5 and 9. So this shows the unique connectrons being sent from the 19 chromosomes to the X and Y. So the X chromosome receives a varied control from the 1 to 19. The Y also receives a little bit less varied control, and the Y mainly sends connectrons to X. At least that's what I've determined. And that's rather interesting. Unique connectron cross-chromosomal matrix is this. Unique connectrons with respect to chromosomes 1 to 19 are roughly proportional to the size of the chromosome, and the texture of the 19 by 19 surface is essentially random or fractal. These are the unique one-shot connectrons, quite a number of them. And so any connectron that turns off its own expression is called a one-shot connectron. All chromosomes have unique one-shot connectrons, and chromosome 4 has the greatest number of those one-shot connectrons. The total number of unique connectrons in a classic Pareto distribution. The intra-chromosomal unique connectrons are also in a Pareto, it's just a subgraph. And then the inter-chromosomal unique connectrons are also in a Pareto distribution. And so this shows the three different distributions there, total. So the number of connectrons for a given C1, C2 follow a Pareto distribution, but the lengths of the loops are not Pareto, they're sort of white or linear. So this is these are the loop lengths in kilobases, and this is the number of such instances. And so you see there's a more or less uniform distribution here. The intra-chromosomal unique connectrons follow the same sort of less than exponential distribution. And then the loop lengths for the interchromosomal are also relatively white. So as a function of loop length, the balance between inter and intra changes. They exchange positions. So there are more short intra-chromosomal loop lengths, and there are more long inter-chromosomal loop lengths. So the conclusions that one can draw from this is that the statistical properties of the redundant and the unique connectrons are similar and uniform and in a certain sense expectable. Even the most fine-grained statistical properties mask the structure and logic of connectron control of gene expression. Rather than using redundant connectrons, one could argue that unique connectrons are probably the correct approach for further analysis. And this is a conclusion I've come to. The MAGE or King graphics on a per chromosomal basis is now complete and shows the intra and interchromosomal connectrons. A complete set of unique connectrons should be used as the basis for simulation of behavior in any transcriptome.